Good morning. Assignment 6 deadline is this Wednesday. And I have also asked TA to speed up the marking. So you should hopefully get a few assignments back this week. Okay. I sent an email on Friday, so hopefully you have seen it. And this is basically the same announcement. We will not set any assignment deadline for next week for the midterm, for the week of the midterm. Okay, and the midterm will be on 14th of March, next Monday, and this will be an online exam with invigilation. So here is the coverage. We want to cover chapters 1 to 6 and partially chapter 7. So for chapter 7, we will talk about, we will cover the open system and the chemical potential part of the chapter. And this is the screenshot of your blackboard. And I would like you to read this as soon as possible here and plan accordingly. And finally, I get the list of students taking this course as well as Professor Emily Ching's course. So I'm sorry for those students, there are 10 of you. You have to handle 2 exams. I really don't know what else I can do. So just, well, I will be accommodating if you show up a little bit late. I will let you in. But for the rest who are not on the list, please show up on time. And I also, for this group in particular, you should read this instruction to see what else you should do in order to, for example, you need to charge your mobile phone. You need to use your mobile phone as a camera for my midterm. So you need to somehow think about how to do this. Okay, so that's all I want to say. Do you have any question? All right, so if not, let's finish the final part of thermodynamics. I want to be quick about this so we can start to play with counting. This is something very fun. So let's see what we covered last time. This is from last lecture. So last lecture, we basically got to this point. The idea is we started to talk about this adiabatic demagnetization as a way to cool to very low temperature, and this is what we covered. So you can think about it this way: if you know the entropy curve for 2 processes that happens at 2 values of a given parameter, for example, x1, x2. Where in the case of adiabatic demagnetization, there will be magnetic field. Okay, just imagine you can have a process happening in x1 and another process happening at x2. So x1 and x2 are different values of the same parameter. You must have something like this, which guarantees that you cannot reach absolute zero. Okay, so the entropy versus temperature must go like this. That's to say, at the absolute zero temperature, your entropy must be equal at 0. Okay, so that is a good thing because that provides a scale for us to do to talk about entropy change. So if we talk about entropy change and then we use the entropy value at the 0 temperature limit as our reference, you can talk about absolute entropy. Okay, so this set a scale, and this is the 3rd law. So again, just like the other laws of thermodynamics, you have different statements, and the different statements come from different viewpoints depending on whether you make the observation in the physics lab or in cosmology or in chemistry lab. You come up with different statements. And some of the very useful one for us to appreciate is the fact that we cannot reach the absolute 0 temperature. Okay, so now let's look at what happens if you have the third law. So if you have the third law, what are the consequences? Okay, so let's look at them. So there are some consequences of the third law. Okay, the first one is the following: you must have all the heat capacity goes to zero. Okay, so that is because the heat capacity is related to the entropy, right? So the heat capacity, let's say we keep it as some constraint x. It doesn't matter which one. So we will write it like this: TDS, like that, right? So this is how we write the heat capacity. If you have constant magnetic field, like what we used the other day, you have C sub B, and that will you change to B. And this is the temperature cannot be zero, but the entropy will go to zero at the zero temperature limit. Or you can write it like this. You can put it in this form, log T, and this has to go to zero. Okay, so all heat capacity must go to zero at the zero temperature limit. So as T approaches zero, so the entropy will vanish. Okay, so this is useful. You will see it very soon why this is useful. And let's go there. Let's keep this one first. Okay, the idea is this: you can kind of use it to justify this statement. The ideal gases are no longer ideal. Suppose you don't know anything about kinetic theory of gases. This is not really a thermodynamic. Thermodynamic doesn't care about the details. So kinetic theory of gases really assume a lot of details about how these particles interact, whether there's interaction or whatever. So there you already talk about a lot, right? The degrees of freedom, whether they can vibrate, whatever. And if you simply think thermodynamically, you can already reach the conclusion that the ideal gas can not be ideal when you approach the absolute zero temperature. Why? Because of the consequence, the first consequence we talked about. If you have an ideal gas, all heat capacity must go to zero. So you can never satisfy this criteria. Okay, so at some point, this has to break down. Right? So at some point, actually, even before you reach absolute zero, you will progressively deviate from this equation. But zero temperature is very easy to see why this must happen. All heat capacity must be equal, and you cannot possibly satisfy this. And therefore, you will not have an ideal gas at zero temperature limit. And actually, the precise statement should be like this: as you cool down, ideal gas can progressively deviate from the ideal situation. Okay, and to understand why, then you need to learn more about your system, and that is when you should bring in your other knowledge beyond thermodynamics. So thermodynamically, this is the best you can do. Okay, and the answer is you can also be very quick about this. When you try to go to lower and lower temperature, you can no longer ignore the interaction, and that interaction is what gives you the real realistic picture. And whereas when we do thermodynamic, we ignore those interaction. We just say there's a volume, and this volume of matter turns out to be gas particle, and then we can play with the volume. We can use pressure to control it, and so on. Okay. And the other thing here, this is thermal expansion, something we learn, something we define, that also has to stop as you approach the zero temperature limit. Perhaps here it's not immediately obvious. Now, if you did, this is how we define thermal expansion coefficient. And how do we link it to the entropy? The answer is you use the Maxwell relation. Perhaps the value of this example is for you to see that Maxwell relation is again playing a role when we do thermodynamics. Okay, so if you link this partial derivative to your using the Maxwell relation, you know how the entropy should change. And the idea is the entropy change will goes to 0 for any process when you approach t equals 0, and therefore this beta has to be 0 as well. Okay, which means the thermal expansion eventually it will slow down. Right? We know it will slow down. Actually, we know it will slow down, but at the 0 temperature limit, it will be precisely 0. Okay, so I don't know whether you know all this data. Now, thermal expansion, when you cool something, volume changes. And if you know this curve, it will start with some very fast change of volume. And as you approach a 0 temperature limit, it will become flat. In my office, I actually have some thermal expansion curves, which it look really like that. At the low temperature, you cannot really gain too much from shrinking. You cannot really lose too much volume when you reduce the temperature. Okay, and that is this physics here. Okay, in my office, I have this curve because one of my students is working on this thermal expansion project. So he used some material. Let's imagine you have a piece of paper, okay, in the form of a sheet, and that will shrink when you cool down. So he put some superconductor on this piece of paper, and then he used temperature. He simply cool it down to see how this shrinking of the substrate, the base, will kind of change the property of this superconductor. Essentially, this is what we call, it's a bit like applying pressure, but in the 2D sense. You stick a material on this active paper, if you like, and this paper shrink very violently, and what happens to the material you put on top. So we use this, the student used this property to study what changes when you carry on this process. Okay, so this is something, that's why I have this table. I have this graph showing the thermal expansion coefficient of many materials in my office. Okay, and next thing is this here. The Curie law should also break down. This you can see. This one is kind of derived, right? We did this. Remember, we derived this equation last time. This is the prerequisite for us to discuss all this adiabatic demagnetization, adiabatic cooling. This is part of the stories. And then you see this Curie law. This is built on Curie's law, right? The left-hand side is related to this this derivative, which we know has to be negative, right? Because we have this result. Chi is inversely proportional to temperature. And the idea is this: when you approach the 0 temperature limit, this has to break down. Why? Because this is related to the partial derivative on the left. And this partial derivative of the left has to be 0 when you approach 0 temperature limit. And therefore, this Curie law cannot go on forever. You can go to very, very low temperature and eventually it has to flatten off. Okay, so this is when this guy, this is really the slope of this curve when you plot chi versus t, right? So you have chi versus t, chi. Curie law tells you have something like this. And when you go to low enough temperature, it has to flatten off. Okay, so this is the reason. Okay, and again, why do we have to why do we have this picture? And this is some explanation. This explanation again has to do with further knowledge about the system. It's beyond the thermodynamic level, but thermodynamic tells you must expect some kind of flattening, and your task now is to find a way to explain this. And the reason is the same. Interaction becomes important, and when we discuss Curie law, we have the notion of independent moments. And when we do statistical mechanics, we are going to neglect the interaction and we are going to do independent moments. And that is something I promise you. I told you we are going to see this Curie law once again when we do statistical mechanics. Okay, and now you can keep in mind that the third law tells you what happens in the limiting case, and we are going to be able to get some result at the finite temperature regime. Okay, and finally, this is also very cool. This is about the phase boundary. Remember your Clausius-Clapeyron equation. You have this change of entropy coming in. Okay, and this change of entropy goes to 0 too, right? Because it doesn't matter what kind of process, as long as you go to 0 temperature limit, your entropy change has to be 0. And therefore, if you look at this first order transition, the phase boundary, right? This dPdt describe, let me remind you, this describe the phase boundary, the slope of the phase boundary for a first order transition. Okay, and if you look at this, this is a nice picture. When you go, if you have a first order transition, you are governed by this equation. And if you look at the PT phase diagram, this is one example. And when you go to 0 temperature limit, this slope has to be flattened. This is governed by third law as in conjunction with the Clausius-Clapeyron equation. Okay, so this is why you get this horizontal slope. Now, this is a very fascinating material. This is liquid helium. And I'm sure you have seen some discussion in the exercise class. And this is, we use it for cooling. And this is the pressure scale. Okay. And in the lab, we are at 1 bar. 1 bar is about 0.1 MPa, megapar. So it will be somewhere here. Okay, so 1 bar is somewhere here, and that's why the boiling point of helium is 4.2 Kelvin. And here you cannot really distinguish between gas and liquid, and therefore there's a critical point here. So this is the critical point C. And how do you stabilize the solid phase? And this is the interesting part about this material. If you keep cooling, you cannot stabilize the solid phase. You actually enter the superfluid phase. Superfluid is a bit like superconductivity, but you rather than having electrons in the material flowing without resistance, here you have fluid that is flowing without any viscosity. So this is a superfluid phase. And if you want to create solid, you have to apply pressure and cool down at the same time. And this is where you have the solid phase. And you see, this is another example where you have polymorph. This BCC means body center cubic. So there's a very narrow region where you can stabilize one type of solid structure, which takes the symmetry of body center. So this is body center cubic. So it's a cube. The unit cell looks like this. You have a cube. And then in the center of the cube, you have another site. Okay, so this is called a body center. BCC is body center cubic. And this one, HCP, this is called hexagonal closed pack. So this is hexagonal closed pack. Okay, HCP. This HCP is related to another cubic structure. And this HCP, the best place to see this is if you go to a supermarket. These days, if you go to supermarket, you see how they stack up oranges. And that kind of structure is related to this hexagonal closed pack. So if you view from the top, let's say you go to the supermarket, you see how they stack oranges, and you view from the ceiling. and you see clearly why this is the closed spec structure. So if you view from the top, let's say you view from the top, you see something like this. You see all these oranges are doing this kind of packing from the top layer. Okay, and then this HCP requires you to this is one layer, right? This is the top view, and then you take another layer like this and then stack on top of this. Okay, so you can, for example, you take another layer. So this is the center. You take another layer and you move. You have other place to put the center. For example, you can put this void here or this void here. You can put it on this void or this void here, and that will give you this kind of stacking is related to this closed pack, and it depending on how you stack them. If you stack like this A, if you call this A, and you call this B, and this is C. Sorry, let me B, and this is C. If you stack A, first layer is A, you have no choice, and the second layer you put it on the void labeled by B. And the third layer, you have the choice again. You can either go to A or you can go to C. So if you do this AB, AB, AB stacking, and this is called the HCP. If you do this, if you do A, B, C, A, B, C, and this is called the phase center cubic, FCC, phase center cubic. Okay, and that is related to this, but rather than having one additional atom at the body of the cube, you have another additional atom. Now, FCC, I would draw for you. This is FCC. You still have your cube, but you will have in the center of the face. This is the front face. At the center of the face, you have additional lattice site. So you have one here, and the top face, in the center of the top face, you have another one, and the center of the left face, at the center of all faces, you have another one. So this is another structure. Okay, so this is something you will learn in solid state physics. It's fun stuff. I really enjoy talking about this, but we have to move on. Okay, so I think my message for you is here you should understand that the phase boundary at the zero temperature limit has to be horizontal, and then you can see a different structure in the solid state, and this is called a polymorph. Okay, this kind of tie up everything I want to talk about. All right, so that is the end of thermodynamics part. It doesn't mean you can forget everything, because I'm going to first, as mentioned, I will come back to Curie law, and I will use the fundamental relation in thermodynamics again and again. Okay, so something we should keep in mind. All right, so now let's begin chapter 8. This is week 8. We are going to do chapter 8. So the progress is good, and I'm very happy about this. We have about now this is week 8, right? So we should have 11 lectures left, and we are going to use one for midterm. So we have about 10 lectures left. I think I should be able to cover a lot, and if I cannot, don't worry, I will make up. Wow, and for online teaching, makeup is very easy for me. I just sit in my office, and you don't even need to come. I will give you the video. Okay, in case there is something that we need to do, I will do it that way. Okay, so this will take about 10 to 11 lectures. It should be enough for us to do this. So now, the design of this course is to do the thermodynamics properly, and then we do statistical mechanics to see what we can relate to different parts. And if you want to learn more about statistical mechanics, you can go to the next course. Okay, so we have the next course in 4000 level, and that will talk about statistical mechanics, almost entirely on statistical mechanics. Okay, so let's begin. What have we learned so far? What we have learned so far up to this morning, up to 2 minutes ago, was equilibrium description of our thermal system. Okay, equilibrium and macroscopic. Now this term will show up a lot from now on. Macroscopic. Okay, so this is an equilibrium macroscopic thermodynamic description of our matter. Right, so this is thermodynamic description. Okay, and I'm sure a lot of you have taken quantum mechanics, or you are studying quantum mechanics. So that is the other extreme. So in the other extreme, we have microscopic. Our microscopic world is described by quantum mechanics. Right, very small, very big. We kind of already have quite a lot of success to describe our big systems. Okay, piston cylinder system, a magnet, rubber band, open system. All these are big systems. And when you go to very small, you have all these QM descriptions. And the purpose of this part of the course, I think, in my opinion, I would also like you to view it this way, is to really provide a link, a bridge between these two extremes. So this is where we do statistical mechanics. Okay, so therefore, naturally, I want you to not just to come to my course and ignore other people's course. You should keep in mind what you have done in other courses in quantum mechanics. In particular, I'm not gonna do quantum mechanics. I will do a bit. I won't do a lot. I'm not going to solve a lot of Schrodinger equations. I just assume you have done it. So I assume you come to my course with all these ingredients. Okay, what are the ingredients? So the ingredients are this. You have all the discrete energy levels, right? So this is the outcome of your manipulating your Schrodinger equations. Right, so I'm not going to talk about in those courses. You talk about different kind of potentials, different kind of boundary conditions. We are going to do something like this, but I'm not going to do a lot. I'm not going to, in particular, I'm not going to talk about the mathematics of Schrodinger equation, right? So I just want all these energy levels that you have done, you have solved, you just bring to me, and I'm going to use it to try to get to the thermodynamic description. So what are the thermodynamic description? For example, we care about the internal energy, we care about heat capacity, we care about the volume, we care about the all these thermodynamic quantities you have learned before, right? So for example, heat capacity at constant pressure, etc. Right? Okay, so I'm going to use this large number of energy levels. Now, sorry, I take it back. The energy level might not be large, but we are going to assume we have a large number of particles. I can have only 2 energy levels for each particle, but I want a lot of particles. And that is useful because I'm going to talk about statistics. So I need a lot of a large system now. So this large number actually helps me. It helps me to come up with a way to go from here up to the thermodynamic description, and that is the language of distribution. Okay, we are going to come up with distribution functions to describe different scenario depending on the property of these particles. Are these particles fermion? Are these particle boson? Or is there a way that I cannot tell whether a particle is boson or fermion? Is it possible to have a case like this? And how many distributions I can come up with? Okay, so this is the M. Another thing to keep in mind is this: we are not going to worry about the interaction. This is important. Before I just say like this, it's just like you might think, this is a simplification. We don't want to talk about interaction. But now you need to ask why. Okay, so this course, we are not going to worry. We don't want to focus on interacting case. Okay, now for this part, this statement means when I write down the internal energy of the system, the internal energy has a simple form, which allows me to move very far. If I need to worry about the interaction, the internal energy will depends on the energy of the particles itself and the interaction with other particles. So that interacting term has to be modeled very carefully. Okay, and that depends on the situation, whether you have a magnet, whether you have a gas of atoms. That will be very different for different cases. Okay, so we are not talking about them, and the reason is this: is the fact that the interaction, the internal energy can be very elegantly written down. Okay, so when I write down the internal energy, I want you to realize this fact. Okay, and then we are also not going to discuss. So these are not going to discuss the ensemble theory. Okay, I'm going to only choose one particular ensemble. You don't, because we don't talk about ensemble theory, you might not even need to know about the name of this ensemble. So I'm going to write this down for the students who have seen something like this, or for students who will see this in the future. So we are going to use this ensemble. This is called the micro-canonical ensemble. Sorry. Okay, so this is an ensemble we are using. You don't need to worry too much about this, but you need to know what is the constraint for this ensemble. So I'm going to write this down for you. This is an ensemble with a fixed total number of particle m, with a fixed total internal energy U, and a fixed system volume V. So this is called the micro-canonical ensemble. Okay, so in the case of thermodynamic, we call this isolated system. Now this fixed V is particularly important. This fixed V will simplify our life. When you come in with this discrete energy level, you solve your Schroeder equation. You solve, for example, let's take the simplest picture. If you solve this particle in a well, you get your energy eigenstates. You get E, characterized in terms of principal quantum number n. If you go back and look at this expression, you find that this E sub n, now you might think this is related to n only, but there's something implicit, right? That is something we should realize, and that is the size of the well, A. If you change the size of the well, you change the you change this expression. That's to say you change the spacing between the energy levels, and that will complicate the situation. We can deal with this, but this is the kind of mathematics that will not give us a lot of physics now at this level. So if you fix A, your energy spectrum is fixed. then you do not have to worry about suddenly this energy spectrum is changing and you have to recalculate your internal energy. Okay, so that is sometimes students don't appreciate this fact. They ask, why do we care about constant volume? This constant volume, if you go to the 3D well, this is essentially the same problem, right? The size of the well will adjust the energy spacing. Okay, so I want the spacing to be unchanged. So I want my V to be a constant, volume to be a constant. And to be very, very precise, I also want to say something about this interaction. We do not want to worry about the interaction, but without an interaction, you cannot have thermal equilibrium. So we are going to take this to be very weakly interacting. So more precisely, we work on weakly interacting case. Okay, how weak? Weak such that we don't have to worry about this term in the internal energy, and strong enough, sufficiently strong for thermal equilibrium. That's it. So you can just view this as a philosophy, right? We really want, if the particles do not talk to each other, you cannot really talk about thermal equilibrium here. Okay, so this is our plan. This is what we want to do. And how are we going to do it? So this is my proposal. I'm going to look at, before I start, I also want to say that I would try to make the note self-contained, which means you do not need a textbook. The textbook, if you look at Blundell and Blundell, this is a very good book, but this book talks a lot about ensemble theory. So you need to be careful. So if you refer to my note, you will have the treatment done in the microcanonical ensemble, only one ensemble, such that you don't need to worry about ensemble theory. And you'll be able to get a lot of results from my note already. I do recommend some textbooks. They are listed there, but you don't need to buy them. Okay, and that's what I want to say. And those are the books now there are many sources. I read a few books to come up with these lecture notes. So I hope my notes will be self-contained for you. Okay, so now the most important example is the example of flipping coins. Okay, so this is the system. I want you to pay attention and then to see how to synthesize your knowledge for statistical mechanics. So this is what I want to do in great detail, so you know how to deal with this kind of problem. The coin, I'm going to take 4 coins. So these 4 coins are distinguishable. So you are able to tell which one is coin 1, which one is coin 4. Okay, so we are going to look at distinguishable coins. And now I take 4 of them because this system size is small enough for me to write everything down. Okay, so I'm going to take 4 coins, or you can also think of it this way. I can also take 1 coin, but I flip the same coin 4 times. Okay, so this is the same situation. I can flip only 1 coin 4 times. Okay, and these are identical coins, and then they are even. Okay, so the probability of getting head or tail is equal. It will be a half. Okay, this is really our toy model. This is the entry ticket for learning statistical mechanics. So this is our toy model. Now, toy model is not really something for you to, it's not just coins. You should think about it a little bit deeper, right? So this is really the model for distinguishable particles. Distinguishable particles. For example, the mathematics of coins is identical to the case of spin 1/2 particle. If you have spin 1/2, you have only two possibilities, whether you have head or tail, but you don't call it head, you don't call it tail, you call it spin up or spin down. Okay, so how do you make all these spin half particles distinguishable? This you can have some trick, right? So now we are going to talk about distinguishable, and then about 2 weeks later, we are going to begin to talk about particles that lose this feature. Okay, so now keep in mind that we want distinguishable particle. If I have all these spin half particles, how do I make sure I can distinguish them? It's not that difficult. I will come up with, I will draw the same picture for you. I can put a lattice, and I can, now this is my cubic lattice I drew earlier. If I have a lattice, I know the address of all these points. So I'm going to do my analysis based on the lattice, and I'm going to put all these spin half particle here on all these sites. That's to say, this particle is not the same as this particle. They are on different sites. I know the address of the site, and I will be able to use I will be able to use the coin model to describe this situation. Okay, so this coin model is not as innocent as it looks. It really goes very far. All right, so if you have 4 coins, what are the possibilities? I'm going to use this notation. I'm going to say, okay, I flip it the first time, I get a head. I will put H, right? This is a head. Okay, and I have 3 more times. Maybe I get head. So this is one possibility. Okay, and I can have other possibility, as you know. I can have head, tail. I can have head, tail. This is another possibility. And then I can also have tail, head, tail, and so on. Okay, now the point is, in principle, you are asked to list all this, but in practice, if the system size is big, you are not going to do that. That's why you need statistics. Okay, so for 4 coins, you can actually do it. For 4 coins, you can try to list them. Before I go there, let me define a few terminology. These things are called microstates for this coin problem. Okay, so you have 1 microstate, 2 microstates, 3 microstates, 4 microstates. I have shown you 4 microstates. Okay, on this on my big paper, you see 4 microstates. So this, sorry, let me make it longer. So from here to here, these are microstates. Okay, and here you see they are I have shown 4 microstates. I will use this symbol. Okay, microstates. Okay, so HTTT is not the same as THTT. They are different microstates. Okay, so now the question for you, I want you to type, how many microstates do I have for this problem? This is something you must be able to do. So just do a little bit of a warm up. Tell me, type to me in private, so you don't influence others. How many microstates do I have? And this is a kind of thing I want very, very quickly. Thank you, thank you, thank you, thank you. Okay, so I have for the first flip, I have head or tail. For the second one, I have head or tail. For the third flip, I have head or tail. So all together, I have 2 to the 4. Because this is independent event, I write them up like this. So I have 2 to the 4, 16. Okay, so I have these independent events, and collectively, I will have 16 different microstates. Okay, now I want to ask the question differently. Listen carefully. Listen carefully. I want to ask about this scenario. I want to have, how should I write? I use different color. Okay, so I want 3 tail, 3 T, and 1 head. Okay, now this is what I want to observe. And in this case, it doesn't matter whether it's this scenario or this scenario, right? So I have 3T, and then I have 3T. All right, I hope you begin to sense what I'm going to say. Okay, now this one is a particular macro state. So this is a particular MA. This is a macro state. Okay, I want to say, for example, I take a box, I put 4 coins in, I shake, and I do thermodynamics measurement. What do I measure? The measurement I do is the number of tail and the number of head. And I want to ask myself, what is the likelihood for me to see 3 tail and 1 head? Okay, this is my macro state. And in this case, for this particular macro state, both star and star contribute to this goal, right? This is what I want to this goal. What is my goal? My goal is to ask myself how to achieve 3 T and 1 H. Okay, and therefore in the language of statistical mechanics, both of them, okay, because both belong to the same macro state. This is an A again. Okay, so now the picture begin to emerge, right? So the picture is this. This is what I want. Now this is from the note, from your note. You have it. This is the macro states for this coin problem. I check my box for distinguishable coins. I open the box to do the measurement, and I want to ask how many heads do I get? Okay, so if I get 4 heads, what is the chance of getting 4 heads? I'm not saying that you cannot. You still have a chance to see it, right? For such a small system, this is exactly the point, right? So you have 1 out of 16, right? The occurrence of the frequency of HHHH is 1. But the point is, if I want to have 2 heads and 2 tails, you will have more possibility to see it. Just like thermodynamically, why do you see this particular result? The reason is this: if you think in terms of statistical mechanics, there are simply more ways for you to achieve a particular thermodynamically observable result. Okay, there are more ways to do it. So this is really an interpretation in terms of probability. So for such a small system, it's hard to really argue too much, right? So you have the frequency. Now this is called the frequency. This column here is called the frequency. It tells you how many different ways you can get two head and two tails. Okay, so you have 6. And if you sum them up, this gives you 16, right? So let's check. So this is a 10. This gives you 16. But not 1. And that is why this is called unnormalized probability, because they don't sum to 1. But they do still give you a sense how likely a given macro state is probable. Okay, so this is called thermodynamic probability, unnormalized probability, or you can call it the frequency. And the point is, based on our usual experience, we know that if you have a large number of coins, let's say you collect 100 coins, you put it in the box and you check, you it will be very, very unlikely that you get all of them, all 100 of them to be head. Okay, and most likely you get around 50 of them head, or not too far from that, 50 head, 50 tail. Okay, and that again is related to this kind of argument. Okay, so this leads us to 2 important postulates. You see, we are already making a lot of progress by studying coins. So those are the 2 postulates of statistical mechanics. So postulate 1. Okay, so for a system in equilibrium, all microstates, this is an I again, all microstates are equally probable. Okay, so all this, everything here, all these 16, each and single one of them are equally probable. Okay. Then how do you talk about what you observe? So that is postulate 2. So the postulate 2 is this: the observe, what you see in reality, the observe a macro state A, again this is an A, is the one with the most microstates. Okay, now this is before quantum mechanics. All this came around the time of Gibbs and in particular Boltzmann. So they already began to think in terms of probability. You might think quantum mechanics is what introduces probability to physics, but this is pre-quantum. Now I talk about all these energy levels. Imagine you have a way, now all these coins do not really require me to solve quantum mechanics, but the philosophy, the idea is already there. So these 2 statements doesn't really require me to solve quantum mechanics. Later we will see energy states, and this is best solved by, best provided if you know how to model your system very precisely. And that is the role of quantum mechanics. If before that, if I know how to write down the energy levels, I can already formulate all this. It's just the result might not be accurate. But for the coin problem, I get very precise results without knowing anything about quantum mechanics. I could go to a high school public lecture and talk about the same thing. Okay, so now that is one comment, and these 2 are important. There's another one coming. And here, I want to make a comment about this system size. Now, for that system you saw with 4 coins, it's very likely for you to get all head. It's not completely nonsense. If you get head, I won't be too impressed. I will be to some extent. I would say, wow, you're so lucky today. Today is your lucky day. You should go and buy lotto or something like this. But I won't be too surprised. Now, this is something to do with the system size. If you look at that distribution, it's actually none of okay. I will plot that distribution for you. So what do I have? I have 1, 4, 6, 4, 1. Okay, if I use the number of heads as my independent variable, right? So if I do it for you, I have 1, 4, 1. Let's say I put 1 here. 1, 2, 3, 4. 1, 4, 6, 4, 1. Okay, so this is the histogram based on that problem. Right, number of microstates is 1. Right, I use the same. I don't normalize, but I use the number of microstate as my vertical axis, and I horizontal axis. I would just do the number of head. Okay, it's a same axis. Don't want to write it. Okay, so for example, here you get H. Occurrence is 1, frequency is 1, and here you get tail. Now look at this. This is nowhere near any of this here, right? Because you don't get 0 at all. In principle, you won't get 0. It's just a very small number. But look at this, how broad this is. This is something to do with the system size. Now, you might feel uncomfortable about this. I would like to reassure you that our goal for this course is to deal with large N. So when you have large N, this is the direction of increasing N. Right here, this is a small n equals 4. 4 coins. Okay, if I have 10 to the 23 coins, I will get a very sharp distribution. So this distribution will sharpen up very quickly, such that you will most likely get half of the coins to be head, half of the coin to be tail. Okay, and it turns out that this large system is our real thermodynamic system. Okay, so this is a small system. I can write it down for you, and I propose a break, and after the break I'm going to go analytical and show you how to do optimization. Okay, so let's come back at 12:40. Okay, so just enough for you to maybe take a break, go to toilet. Okay, see you soon. Welcome back. Okay, let's continue. Right, so real thermodynamic system, real system. Let's say we take a piece of gold or copper or a typical system that you can see. How many particles do we talk about? So the purpose is to really keep in mind that when you have a very large number of particles n, this is a really sharply peaked distribution. Okay, and that will give us some additional advantage when we do mathematics. Sorry, here. Okay, how many particles do you have? If you have, let's say, if you have 1 centimeter times 1 centimeter times 1 centimeter cube of copper, you will have about, it's a convenient number. We should remember the number of particles is about 10 to the 23. Okay, it's about Na. So you have Avogadro number of particles. So this is in a typical, this is order of magnitude, so we don't care about the number, the exact number. I just want you